Alright, another network which is used in practice is called the tree network. This is a very simple network, okay, and typically we talk about binary trees, and so a complete binary tree you will have something like this, right. Now there are two ways in which you can build the tree. One is where these internal nodes, these are also nodes, right, what you see over here inside the tree, the internal nodes of the tree, they are also nodes, right. And in another setting, only the leaves are the nodes, right, and in that case your internal nodes are actually more of switches, right, they are just doing the work of forwarding the data, they are not actual nodes. So again we can get into analysis of both, they are not very different, so we'll just get into one, right. So let's just talk about the case where all the nodes are at the leaves. Yeah, so we'll just assume that there are p leaves, right, and all the other tree nodes serve as switches, right, or routers or forwarders. Okay, so this one I think we can analyze without even looking at it, right. So let's just go to the chart. What is the number of links in a tree which has p leaves, complete binary tree?
P plus P by 2 plus P by 4.
Yeah. So roughly about 2p, approximately. Yeah. It's obvious, right? At the leaf level you will have p edges, the next level you will have half and then half and so on. Then what is the degree? Well, degree is 1. Yeah. What is the diameter? So you need to go from a leaf all the way to the root and then come back all the way to a leaf, right? So that is 2 log p, roughly about 2 log p. And the bisection width, how many edges do you need to remove? 1, right? You just remove one edge and you're done. Okay, so the features of a tree don't look that great, but it's a very simple network. So people have modified this and come up with another architecture which is called the fat tree network, which is actually used heavily in practice, right? And what is the fat tree network? It's quite simple again. The great thing about the tree is it's easy to set up, unlike hypercubes and fully connected, right? Yeah, so what do you do in a fat tree? What you do is that as you go up, you keep on doubling the number of links. I'm going to add one more link at this level, and at the next level I'm going to add 3 more links, right? Each link has some capacity, right? So essentially, if you have to send a lot of data, if everybody is sending data to everybody else, right, then typically what happens is in a tree, the leaf level nodes are not the problem. The links at the leaf level are not the problem. This guy is sending data up, right, not an issue at this link. This guy is sending data up, not an issue at this link. Suppose that this guy has to send all of this data up, it's double the data, right? And at this level, he'll have to send 4 times the data of all these 2 links as well, right? So the data that is going up is doubling at every stage, right? So that's the motivation to add more links as you go up, right? So you keep on doubling the number of links and you end up with the architecture called the fat tree network. Okay, so let's go back and analyze this. Okay, so what's there in a fat tree? What is the total number of links? Well, at the lowest level I had p links. What about the next level? I had p by 2, but now I doubled all of them. So I again have p links at the next level. What about the next level? I had p by 4, but I have 4 times now. So p again, right? So total is about p log p. That's the total number of links. What's the degree? Maximum degree? Well, the root node, it's not actually a node, it's a switch, but still the degree there is important. Complexity adds over there. So what is the complexity of that switch? What is the number of edges in that switch? There are p by 2 going to the left and p by 2 going to the right, right? Because total is p. At every level, total is p. So the root has two sides. So the total is p. So must be p by 2 on each side, right? If I get rid of any p by 2 of them, I have disconnected the network into two halves. So p by 2. What is the diameter? That doesn't change. 2 log p roughly. You're going to run into ceiling, floor and +1, -1 issues, okay? I'm not bothering about those right now. And finally, what is the bisection width? P by 2. Hold on. What did we discuss here? Degree, right? Oh, sorry. So what is the degree? Degree is p, not p by 2. The degree of the switch is p. That's the max degree. We are interested in maximum degree, right? That's the most complex node. So max degree is p and the bisection width is p by 2. Okay?
So then the max degree for the previous one tree would be 2.
Yeah, sorry. The max degree is 2. Yeah. Good. Okay, finally, the last network, and this is essentially what we've already discussed. I don't think I need to draw it again. So this is your completely connected network, right? Or a clique. So what is the total number of links? Well, every node has p minus 1 links, right? Roughly about p. Let's take it as p. And total p nodes, so p into p square. Every link is counted twice, so p square by 2. Fully connected, you remember, right? Every node is connected to every other node, the one we started with. So if there are p nodes, there are p links going out of each node, p minus 1. And there are p such nodes, so total number of links is p times p divided by 2. Yeah, p square by 2 is the number of links. What is the degree? P. What is the diameter? 1. And what is the bisection width? We spoke about this, it's about p square by 4 roughly. Yeah, p by 2 links on the left, sending to p by 2 on the right, edges to p by 2 on the right, okay? So that's it, that's your complete scenario. So again, completely connected network, hypercube, linear array, these are all of theoretical interest. 2D mesh or D-dimensional torus up to 5-6 dimensions, fat tree, right? These are of practical interest, right? These are actually there.